the next chapter of radical chain polymerization, and in this particular chapter we are going to present a comparative study with the ionic chain polymerization. Now before we go into detail of this particular chapter, let's have a look at what we covered previously. We had an introduction to the radical chain polymerization. Then previously we discussed about the various basic concepts associated with the resonance. Then we performed a comparative study between the radical and step growth polymerization. And if you see that in the previous one we discussed a detailed comparison between the radical and step growth polymerization merits and demerits. Now in this particular chapter we are going to discuss a comparative study between radical and ionic chain polymerization, because both things are extremely important when we discuss about the polymer reaction engineering, especially with the perspective to the reactor aspect. Then we will discuss about the thermodynamic and kinetic aspect of radical chain polymerization in light with the ionic chain polymerization and step polymerization. Then we will have a brief study about what are the effects associated with the various substituents being added in during the course of polymerization. So these three things we are going to cover in this particular lecture. Now let's have a look about a comparative note between the radical and ionic chain polymerization. We all aware about the basic concept note of radical polymerization as well as ionic chain polymerization. Now here we are going to discuss with respect to the selectivity aspect. Now selectivity towards a specific kind of monomer. Now you see that in this particular figure this chain polymerization is subdivided into two different streams. One is radical polymerization, another one is the ionic one. And furthermore, the ionic polymerization or ionic aspect is again subdivided into two broad spectrum. One is the cationic one and second one is the anionic one. So by this figure the things should be clear in one's mind. Now let's have a look about the selectivity aspect with this with the reference to the specific monomer. Now ionic polymerization is a monomer selective polymerization. So based on the specific type of monomer, it can be polymerized through a specific kind of ions, those who are having the capability of promoting this polymerization. Now this depends upon the resonating character which we discussed earlier in the different chapter. So this resonating character is induced with specific functional groups. So if you recall that we discussed this particular approach in the previous lecture, that what are the different type of resonating characters and what is the impact of those resonating character with respect to the functional group. Whereas the radical polymerization, it can be usually used to polymerize most of the addition polymerization species. So this is a selective node with respect to the selectivity aspect with the specific monomer. Another thing is which is related to under the head of comparative note, that is the propagating species. Now both radical and ionic polymerization proceed in three steps. One is initiation, propagation and termination, which we had a long discussion with respect to all three steps of polymerization process. So both means radical and ionic chain polymerization, they use the different kind of propagating phenomena. Now in radical polymerization, the propagating species is a free radical, unpaired valence electron, while ionic polymerization, the propagating they propagated either using the carbanium ion or through carbon ion. So you can see here there are different approaches of molecular structure like nucleus, electrons, orbitals. Now here this particular point is very attractive with respect to the free radical. Now this is the missing electron. Here if you recall the previous lecture where we discussed about the ionic as well as the radical concept, here the missing electron over here, it creates a free radical, and that free radical is highly reactive in nature. So, this is the you can say the difference between the radical and ionic chain polymerization. Now, as ionic polymerization is specific, hence both of these species require a specific type of monomer, maybe cation or maybe anion. So, that is a very important thing which need to be expressed, because they are very much monomer specific. So, whenever you require any kind of a specific polymer product, then definitely you have to be very choosy according to the monomer aspect. And in that case, if you are going through the ionic polymerization route, you must remember that this particular route is monomer specific. Now, based on the type of monomer, we can differentiate between the radical and ionic chain polymerization. Radical polymerization, it can be occur on almost all vinyl or ethanyl monomers, whereas the cationic polymerization, they requires the monomer having the electron donating functional groups, which we discussed earlier, if you recall that it was plus R effect. And ionic polymerization, they require monomer having electron withdrawing functional group. If you recall, that is minus R effect in the previous one. So, this is a comparative note among radical, cationic, anionic polymerization. Now, sometimes another parameter which is having very important while discussing about the comparative note, that is the effect of solvent polarity. Now, effect of solvent polarity is again very integral part if you wish to distinguish between these two polymerization system. Now, in radical polymerization, it is independent of the effect of solvent polarity. That is very important thing. And in ionic polymerization, the reactivity of ion increases usually with increase in polarity of the solvent medium. So, it is very selective about the solvent thing. Now, when it increases with the increase in the polarity of the solvent, now this particular concept results in high rate of a reaction and getting polymers with higher molecular weight. So, this is a very important thing while deciding that which polymerization scheme would you like to have on. On the other hand, if high polarity solvent, they can also react with the initiator, and sometimes they may stop the reaction. So, that is why this particular thing is very important while deciding. Sometimes by mistake or by any experimental approach or hit and trial method, sometimes it may create a problem, because these high polarity solvent may get associated with the initiator, and your polymerization reaction will truncate without any initiation. So, these are the certain high polarity solvents like water, alcohol, etc. So, the solvent with the moderate polarity is usually preferred. So, that is another concept which we need to take into account. Another important factor is that is the nature of reaction. Now, radical polymerization is a simple and moderate kind of a reaction. It is also not very sensitive towards the various impurities associated with within the reaction mass or reactant, etc. And it also usually does not require any kind of a catalyst to proceed the reaction faster. So, these are the things which are related to the radical polymerization. Now, if you compare with the ionic polymerization, which is a complex in nature and a very fast type of a thing, about you can say 10 to the power 5 times faster than the radical polymerization. So, it is very sensitive towards the impurity like water, if we discussed in the previous slide. Now, if it is present in the reaction, and then it may kill the initiator, and it may kill the entire desired polymerization process. And this ionic polymerization, it usually requires co-catalyst to obtain the desired product. So, this is the comparative note with respect to the nature of a reaction. The termination step also plays a very vital role if we wish to compare between these two polymerization system. Now, in radical polymerization is usually terminated through any kind of a bimolecular type of termination protocol. Now, to be more precise or to explain all those things, so when the two radicals combined with each other to form a neutral polymer chain. So, this is the radical polymer and this is the radical polymer. If they combine together, then they truncate the polymerization reaction. However, the polymerization, ionic polymerization always require an external agent. That is important thing to terminate the process. Sometimes maybe with the help of a quenching with water, because you see that water, because of the polarity of the water, it may react with the initiator to stop the reaction. So, sometimes it may require to quench with water, or sometimes the addition of water or any kind of a solvent may play a vital role. Now, this concept is just can be explained with the help of a small thing, that this is attributed to the fact that like charges, they repel each other and hence cannot form a new bond to terminate the reaction. It is just like that both of them, they are having the like charges and they cannot come together. So, they are far away, and that is why they promote to the termination aspect of the polymerization reaction. Another, so therefore, the ionic polymerization is also termed as the living polymerization. Now, if we add more and more monomer to the reaction mass, then it will again start propagating in a similar manner. Now, let us have, by this way we discussed about a comparative note between the radical and ionic polymerization. Now, let us have a look about the thermodynamic and kinetic aspect of radical chain polymerization. Now, the condition that any specific monomer, it can be transformed or to polymer depend on the aspects of both thermodynamic and kinetic feasibility. In the previous lectures, we discussed about the impact of thermodynamic character with respect to the exothermicity and endothermicity and the kinetic behavior of various kind of polymerization reaction. So, these two aspects plays a very vital role in every kind of polymerization reaction, and that is why the radical chain polymerization we are going to discuss over here. So, under any and all condition of a reaction, polymerization will be impossible unless it passes the thermodynamic feasibility test. There are various thermodynamic equations associated with this type of a concept. So, if it fails in the thermodynamic feasibility test, then there is no point to carry out any kind of a polymerization reaction under the given heads. So, thermodynamically, a feasible chemical reaction is a chemical reaction or a reaction which, when proceed in forward direction, result to a decrease in free energy, that is the Gibbs free energy of the system. So, this means that a monomer will only convert to the polymer if free energy change delta G. Delta G is the Gibbs free energy, delta G is negative. That is the universal fact that need to be accounted. Now, negative Gibbs free energy is the desired condition of any chemical reaction to proceed, but polymerization can only occur if reaction is kinetically feasible. We have discussed a broad spectrum of kinetic study of these polymerization processes. So, in other words, a chemical process or reaction is feasible when a chemical process proceeds at a realistic pace. So, one handles with the theoretical aspect, another one handles the practical aspect. So, the feasibility again is tutored by this kinetic approach. So, the polymerization of a very large variety of unsaturated monomer is usually thermodynamically feasible. A very specific condition of reaction are often needed to achieve kinetic feasibility in order to achieve a particular polymerization. So, that is a very foremost and very important part which we need to encounter. Now, while radical cationic and anionic initiators are used in chain polymerization, they cannot be used interdiscriminately, as these three initiations forms do not function for all monomers. So, you cannot take the things for granted because sometimes it may not be feasible to use with the line that this will be applicable for all monomers. It is not. So, monomer exhibit varying degree of selectivity, as we discussed in the previous, where we were having different type of solvent. So, they exhibit a varying degree of selectivity regarding the type of reactive center that will cause the polymerization. So, these are the additional factors which one should look into while carrying out any kind of a polymerization process. Most monomer with the radical initiator may undergo polymerization through varying rates. Monomer, however, they show the high selectivity against ionic initiator because of the availability of those ions in the initiator. So, many monomer with the cationic initiator they do not polymerize, whereas other may not polymerize with anionic initiator. So, this particular approach is a case sensitive approach. So, based on the different type of a scenario, it can be achieved. Now, the form of initiation that introduce polymerization to high molecular weight polymer of different monomers are indicated in different table. Now, you see here there are various chain polymerization occur by the different type of initiator. You see one column reflects the different type of a monomer. Then there are the classes of initiation processes like ethylene. It can go with the radical polymerization, but cationic it is not at all feasible, and anionic it is feasible. Similarly, styrene, it is this monomer works for all type of protocols, whether radical, cationic, anionic. Similarly, halogenated alkenes, they are very selective. They work with the radical type of initiators, but they are not comfortable with the cationic and anionic. Similarly, vinyl esters, vinyl ethers, they are having their own parameters of selectivity. So, different type of initiators are being used. Similarly, N-vinyl carbazole and aldehydes, ketones, etc. So, before we proceed further, we must have this type of information with us in a handy form, so that we can design our polymerization process accordingly. Now, if you see that in the table, the monomers, those who are having plus R or minus R effect, like here in this effect, they are containing the functional group favors the cationic and anionic polymerization respectively. Now, if we go for the carbon-carbon double bond in vinyl monomers here in the table, then CO double bond in the aldehyde and ketone are the two primary forms of bonding that undergo chain the polymerization. Now, similarly, CO double bond, due to its polarized nature, it is not susceptible to polymerization by the radical initiators. See, that's just because it is very again case sensitive. Sometimes it may not be feasible and sometimes it may be feasible. Now, both anionic and cationic initiators can polymerize the aldehydes and ketones. Obviously, they must have C double bond O bondings with them. Now, let us have a look about the effect of substituents. Now, carbonyl group, they are highly polarized in nature, but carbon-carbon double bonds, it can be polymerized by both radical and ionic initiator. Now, the distinction occurs, this distinction occurs because of through either homolytic or heterolytic bond breakage, and the pi bond of a vinyl monomer that will react appropriately to the initiator step. Let us have a look about these carbonyl groups. Now, here the resonating structure of carbonyl group is given as C double bond O C. You can see here the plus double bond O. Now, here you see the thing. Now, we can see the polarized nature in such a functional group. So, this is again a crucial thing while we go to this particular approach. Now, let us have a look about the effect of substituents. Now, carbonyl groups, they are polarized in nature, that is why we discussed, but the carbon-carbon double bond can be polymerized by both radical and ionic initiators. the distinction occurs because either through the homolytic or heterolytic bond breakage, and sometimes pi bond plays a very vital role, like in the vinyl monomer. They react appropriately to the initiator species. Now, let us have a look about this particular approach. Now, here these bonds are here. Now, you see here. Now, you see this is this one is homolytic and this one is heterolytic. So, what we were discussing here, that is the heterolytic and homolytic, you can see over here that how they are playing a vital role while deciding the effect of substitute. Sometimes the carbonyl group which are polarized in nature. Now, the inductive and resonating characteristics of vinyl monomer, they decides whether the radical or ionic polymerization will occur or not, maybe with respect to the cationic or anionic approaches. Now, the substituents effect usually they demonstrates itself through its alteration of the electron cloud density, the double bond, and its ability to stabilize the possible formation of either radical, ion or cation approaches. Now, there are other things which are attributed related to the electron donating functional groups. Now, these electron donating functional groups, they increases the electron density over carbon-carbon double bond of the system. Now, this may lead to facilitate the cationic polymerization of the monomer. Let us have a look about this particular approach in detail. The first example is this one. Here we are having this lone pair of electron which is transferred over here. Now, this may become like this. Similarly, the second example is this is the lone pair which is transferred to here, or this is cationic monomer. Now, the functional group, this allows the delocalization of charge. Therefore, the stabilizing the cationic and propagating species of resonance. Now, similarly, we can see this particular approach in various aromatic system. Here you can see this is the aromatic type of approach. Phenyl ring. Now, this is having the resonating structure, or you can form the transfer of charge with respect to Now, here you see that this positive charge is moved over here. Now, another condition, if you recall that we discussed this particular approach in the resonating structure thing. Now, here you see that this positive charge is localized over here. So, this is another approach with respect to the resonance and other thing. Now, sometimes the electron withdrawing is also play a very vital role while discussing this particular approach, and specifically we would like to discuss with the help of acrylonitrile approach. if you see that in the previous example we discussed all those things. Now alkoxy substituent, they allow the positive charge to be localized. If the substituent is not present, that is in ethylene, the positive charge on the single alpha carbon atom will be localized. Now we discussed this particular approach. If you see that the example number 2 here, where the involvement of alkoxy group contribute to the carbocation stabilization through delocalization of a positive charge between two atoms, the carbon and oxygen. Now sometimes the alkyl group usually play a very vital role. They are having the very poor effect in promoting cationic polymerization. Now it is only the 1,1-dialkyl alkene then undergo the cationic polymerization. Similarly, if we see the electron withdrawing functional group, they decreases the electron density over the carbon-carbon double bond. We will discuss this thing with the equation. Now this because they decreases the carbon-carbon double bond, which result in the development of a parallel partial positive charge over the carbon atom. Therefore, such monomers usually they are facilitated by anionic polymerization. Let us have a look about all this particular approach related to the electron withdrawing. Now here you see there are two examples. One is this acrylonitrile monomer. Now here this is shifting towards this one. Now and this is and the second example is attributed to the phenyl ring. Now you see here this the localization of the charge with respect to the electron withdrawing. Now another resonating structure is like this. So you see these are the different approaches. Over here you can see the concept of electron withdrawing over the period of time. Another thing is that stabilization of propagating carbon ion happens by the delocalization of negative charge over the nitrile group or alpha carbon and nitrogen. Now alkenyl or phenyl substituents, if you see in this previous figure which we discussed, that while inductively electron withdrawing can be resonating stabilized the ionic propagating species in the same way as in a cyano group. So therefore, if you see that the monomers such as styrene or 1,3-butadiene, they can undergo both anionic and cationic polymerization. So if you see the previous table where we discussed about the selectivity of these type of polymerization step, these two are the best example. Those perform the both anionic and cationic polymerization in their respective approaches. Let us have a look about these approaches in detail. This is related to the attributed to the radical resonance. Now here the first example carries with this is the cyano group. It's a very popular polymerization reaction, especially used for different kind of industrial applications. Now this is the first example, and second one, if you see the phenyl ring over here, and different type of resonating structure. If you recall that in the previous lecture we discussed, there are 5 different type of resonating structure which are possible for to carry out these polymerization reactions. Now this is the third one. Now if you see, and the fourth one here, this is the charge which is being relocated over the period of time, radical being relocated. Now see 1, 2, 3, 4 and 5, these are the things. Another best example which you can see, and a clearly visible example which is more relevant to the system is like this. And now here you see that this is the example of radical resonance. So these were the 3 examples. They are attributed to this type of polymerization step. Now in the third example you see that we introduced the halogens. So halogen inductively remove the electron. If you see that they remove the electrons and move electron to the resonating structure, but both effects are fairly small. And if you see that the halogenated monomers such as vinyl chloride, they neither anionic nor cationic polymerization. It's usually they are significantly facilitated. So unlike high selectivity which we shown in this previous figure in the cationic and anionic polymerization, the radical initiators such as polymerization of nearly even carbon-carbon double bond are always possible. So when we talk about the radical species, usually they are neutral in nature and they have no specific conditions for either attacking of pi bond or stabilizing the propagating reactor. So they are not having very specific conditions need for. So for nearly all substituents, the resonance stabilization of the propagating radical occurs. So therefore, by delocalizing the radical over 2 or more atoms, almost all substituents are able to stabilize during the propagating reactor. So we were having 4 or 5 different type of things related to you see that there were 5 different type of resonating structures. So you can use all those things as per the choice. Now by this way we are concluding this particular lecture, and we discussed about the various thermodynamic and kinetic studies. We gave a comparative note between the polymerization scheme, and discussed about the various resonating characters of these polymer radicals. Now if you wish to have further studies, then you can have a look of all these references which are listed in this particular slides. Thank you very much.